Hello friends, welcome back to You Can Do TV. $300,000 tons of steel, 330 meters of hull, 2 million barrels of crude in a load. Building a very large crude carrier means splitting the ship into hundreds of giant modules, welding them within 2 millimeters of design, and testing every joint before the ocean does. Here is how one gets built from the first steel plate to open water, and what happens after 25 years at sea. A giant oil tanker looks impossible from the air. Its deck stretches from bow to stern, with almost no end in sight, and the ship you thought was big turns into a fingernail beside it. Try parking that in a driveway. Moving one is another challenge entirely. A hull 330 meters long and 60 meters wide, roughly 297,000 tons of carrying capacity, needs a small fleet of tugboats just to nudge it into position. The tugs look like ducklings pushing a whale, and the whale still barely turns. And the payload numbers stop feeling abstract. 376,000 tons of crude offloaded in one call, close to 2 million barrels, poured from one hull into an entire coastal terminal. That is a lot of gas station. But size is only the first problem. A hull this long has to twist, flex, and cut fuel burn at sea. Newer builds add rigid carbon fiber wing sails that adjust automatically to catch wind while cruising across open ocean. Emissions rules keep tightening every few years. A 300,000-ton crude tanker now has to meet the latest limits on nitrogen oxides, sulfur oxides, and hazardous substances before it earns a voyage. Old designs would flunk on day one. Now imagine 1 week weld on a hull this size. Every loading operation assumes hundreds of thousands of tons of steel will hold. How do you keep errors out of that much plate? Every giant crude carrier starts as a stack of steel plates. 10 to 20-ton sheets arrive by truck, get lifted by magnetic cranes, and pile up in a yard where each plate carries its own identity number. Lose the paperwork and you lose the ship. Moving them is its own trick. A vacuum spreader beam grips a wide plate from above, keeps it dead flat, and glides it across the workshop floor. Drop it once and the panel is warped for good. A shipyard handling supertankers is basically a small city devoted to steel. Rolling machines curve plates for hulls, magnetic cranes swing them overhead, sandblasting booths strip no scale off in minutes, and cutting stations throw sparks day and night. Plates come in raw and leave as ribs, panels, and hull sections weighing dozens of tons each. Workers move between stations and shifts, since some of these plates spend more hours on the shop floor than most cars spend on a road trip. The dry dock at the end just gets the finished pieces. Before any cutting starts, the plates have to come off the trucks. A 30-ton electropermanent magnetic beam grips 50-millimeter thick sheets and lifts them in one clean pass. No slings, no chain marks, no dented edges anywhere. Storing them is where Shipyard gets serious. An automated tower stacks packets of plates by size and grade, then pulls the right one out on command. Try finding one plate in a stack of 8,000 without it. Now the plate meets its first real punishment. Rows of blast wheels fire steel shot at the surface, tearing off rust and mill scale. Then a spray booth lays down protective primer while the plate walks the conveyor. Then comes the cut that decides everything. A computer numerical control plasma torch traces frames, brackets, and web plates out of a raw sheet with an arc hot enough to slice thick steel like warm bread. Miss the line by 2 millimeters here, and a block 20 meters wide will not close later. Big yards run heavy gantry cutters for the thickest plates. A wide bridge glides down the sheet, plasma head trailing sparks, carving out every rib and bracket a supertanker's bottom needs. This is where mistakes get expensive. Every cut edge needs finishing. Grinders knock off slag, chamfer corners for full well penetration, and label each piece so it reaches the right block downstream. Perfect cuts get wasted in wrong stacks, but flat plate is not a ship, it has to bend. A crude carrier's hull is nowhere near a rectangle. The bow, stern, and bilge are all curved, which means flat plate has to be forced into shape. A 3-roller bending machine feeds the plate between 3 heavy rollers and squeezes it into a smooth arc, one pass at a time. Simple idea, 10,000 tons of force. Some panels are worse than a plain curve. Around the bow and stern, plates need saddle shapes that bend 2 ways at once, and no roller alone can do that. A cold-forming press with a shape die pushes the plate against a wooden mold at controlled points, checking the curve against templates after every hit. The operator eyeballs the fit, adjusts the pressure, and repeats until the plate lines up with the design. Get it wrong, and the block will not close later. Get it right, and the ship holds its shape for 30 years. Some rolling machines are downright ridiculous. A 21-meter-long, 40-millimeter thick plate rolling setup can curve a sheet as wide as a small ship section in one pass. That is a lot of steel to talk into a bend. Now the cut plates get welded into panels large enough to matter. On a panel line, sheets are butted, then a submerged arc welder runs a bead down the seam at nearly 1 meter per minute. Dual wire, dual arc, no smoke in the room. Once the panel is one solid piece, a gantry drops T-beam stiffeners onto the surface, and multi-electrode welders tack them in place from both sides at the same time. Automatic straightening machines pull the panel back flat, since heat always warps steel. The panel goes in flat, gets welded 100 times, and comes out flat again. Under every giant oil tanker is a hidden second floor. The tank top sits about 1 meter above the outer bottom, and the space between the two holds ballast water or fuel while adding a full safety layer. Above deck, the same logic applies. The forecastle at the bow, the main deck amidships, and the poop deck at the stern all sit on a lattice of heavy beams welded, ground, and lined up by hand. Cross-section reveals the skeleton. Stiffeners, webs, girders, and an inner hull wrap the cargo in 2 steel layers with ballast between. A skeleton is pieces, the trick is building them at once. Inside every block, thousands of welds have to run perfectly. Robotic welding arms scan the parts, calculate the seam path themselves, and lay bead after bead with no operators standing over them. No manual programming, no fresh setup for every block. Ask a human welder to do that for 8 hours without a coffee break. Some blocks are so big they arrive by barge. A dual-fuel crude carrier with a liquefied natural gas fuel tank made of high manganese steel needs, the tank built as one giant module, floated across the yard and lowered into the hull by a gantry crane that dwarfs everything under it. One lift, one fit, one shot. And then those blocks have to move. A finished hull ring section can weigh several hundred tons, and rolling it across a shipyard is not something wheels alone can handle. Fluid bed transfer systems put dozens of small hydraulic transporters under the block, then adjust each one independently so the load stays level, even if the ground below is not. The system reads the center of gravity of the block, tilts, pivots, and eases the ring into place beside its neighbor. Watching one of these transfers is deceptively boring until you realize the entire bow of a ship just slid across the yard. Zoom out and the payoff shows. All those blocks, engine room, tanks, superstructure, bow, stern, end up as one hull crossing the ocean. Hundreds of thousands of tons moving as one body. Steel plates can be cut, bent, and lifted with remarkable precision, but every one of those pieces still has to become one continuous hull. Welding on a crude carrier is nothing like the weld on a backyard fence. A submerged arc welder buries the arc under a blanket of powdered flux, feeds wire continuously, and lays a bead deep into thick plate. No visible spark, no shielding gas needed. The prettiest weld on the outside means nothing if it did not sink into the joint. Big yards hand the repetitive seams to gantry robots. A robotic arm mounted overhead scans the structure, calculates the path, and lays bead after bead across a hull section. Try running that torch for 12 hours straight. Real parts never match the drawing exactly. Bevels shift, root gaps open, edges are off by a millimeter. Vision-guided welding systems read the actual seam in front of them and adjust the bead as they go. Robots handle the easy runs, but humans still crawl into the tight spots. Ballast tanks, engine beds, rudder horns, back welds under the bow, every awkward corner of the hull needs a welder squeezed into it with a torch. Your gym membership does not prepare you for 8 hours in a steel box. Every finished block earns its ticket by passing inspection. Ultrasonic probes, magnetic particle tests, and radiographic film catch what the eye cannot. Only then does a block get to see the dry dock. A dry dock is not just a big hole in the ground. It is the final assembly line where every block, every keel section, every double hull panel gets joined into one watertight body. A gantry crane lifts hull sections into the pit and lowers them onto keel blocks with millimeter tolerance. The whole ship gets built pointing at the sky. The first blocks landing on the keel decide everything above them. Surveyors set up total stations, laser trackers, and reference points along the dry dock floor before a ton of steel comes down. Once the bottom blocks are locked, side blocks are craned in, then the double hull walls, transverse bulkheads, and the deep girders that run the length of the ship. Every block gets shimmed, measured, welded, then measured again. 2 millimeters off at the keel becomes 20 centimeters off by the time you reach the bow. Step back from the finished hull, and the payoff is a 300,000-ton crude carrier built to meet the latest emission standards. Cargo tanks are more than empty space. They are a maze of stiffeners, hopper corners, and pipe penetrations, aligned with remarkable precision. A crude carrier does not race across the ocean. It grinds across it. The main engine turns slowly, maybe 90 revolutions per minute at full power, but delivers torque numbers most people never think about. Two-stroke marine diesel engines dominate this class because they burn fuel more efficiently at low speeds and hand power straight to the propeller shaft without a gearbox. Some newer designs even run on liquefied natural gas, methanol, or ammonia. The engine bay smells like an oil refinery through a party. Building one takes months and looks like assembling a small building indoors. First comes the bed plate, the steel foundation that carries the whole engine and bolts to the hull. Then the crankshaft drops in. A curved forged shaft as long as a school bus. Frame boxes rise around it. Cylinder blocks stack on top. Connecting rods link pistons 90 centimeters wide, and a turbocharger the size of a car crowns the exhaust manifold. The finished engine dwarfs the workers standing next to it. Modern designs get modeled in 3 dimensions before a bolt is machined. Dual-fuel engines run on marine diesel and liquefied natural gas, both cutting sulfur emissions to almost nothing at all. Getting the engineering into the ship is a whole operation on its own. The engine bed plate has to be aligned within a fraction of a millimeter to the propeller shaft that will connect to it. Cranes lower the engine block through an opening cut in the deck above the engine room. Workers on scaffolding align the mounting feet, check the level with laser trackers, and torque bolts the size of a soda can down against calibrated loads. Cooling water lines, lube oil lines, exhaust manifolds, and starting air lines all connect while the engine sits there. Miss one step and the whole install shifts. Every major system gets inspected before the engine ever fires. Workers walk the piston chambers, check the cylinder liners, and confirm every valve turns the way the drawing says it should. Power leaves the engine through a shaft, and that shaft is a monster. A propeller shaft on a crude carrier can be over 1 meter thick and tens of meters long, machined on a lathe big enough to swallow a truck. Every surface gets polished, measured, then polished again. 1 degree of misalignment, and the bearings cook themselves. Bearing journals get built up with laser cladding when they wear. A robotic arm deposits fresh material microns thick. Layer by layer, then the shaft is remachined to spec. A 100-ton bronze propeller is where efficiency turns into cash. Even a 2% gain in propeller efficiency saves millions of dollars in fuel over a ship's life. The blade shape starts as a foam pattern milled by a robotic arm, pressed into a sand mold, then filled with molten bronze poured at over 1,000 degrees Celsius. The casting cools for days before it comes out. Multi-axis machining cleans up every blade surface. Robotic grinders polish it, and a blue paste fit test confirms the hub mates perfectly to the shaft. The rudder gets bolted in with the propeller already fitted. Green stands hold it perfectly vertical while workers align the pintles, check clearances, and torque the mounting bolts to spec. A modern flapped rudder adds a second hinge surface behind the main blade. Turning force nearly doubles at the same rudder angle, which matters when your ship weighs 300,000 tons. A hull like that turning gently is still called a hard turn. Seawater does not stop attacking steel for a second. Before the ship touches water, Workers airless spray anti-corrosion primer across every square meter of hull, then layer top coats over it. Paint is not decoration here, it is armor. Ballast tanks get the toughest treatment. Workers in full protective suits crawl through curved ribbed steel tunnels, spraying two-part epoxy coating that has to survive 25 years of salt water without a repair job. Deep in the ship, the engine room runs like a small power plant. Boilers feed steam to enormous cargo pumps. Control rooms track every temperature and pressure, and pipes as thick as a person's snake between the machinery. Every pipe on this ship meets another pipe through a flange. Bolts, gaskets, and machine faces let workers open the joint for inspection, then reseal it perfectly tight. Cargo does not just sit in the tanks. It moves. An oil tanker this size needs a pump room capable of shifting 2 million barrels through pipes as wide as manholes. Hydraulic power packs drive the pump motors, deck manifolds, route the flow through banks of valves, and stripping pumps clear the last few centimeters from each tank at the end of a discharge. Every valve position, every flow rate, every temperature reading feeds back to a cargo control room where an officer works the panel like an air traffic controller. One wrong valve position and the wrong grade of crude ends up in the wrong tank. When the ship travels empty, ballast water keeps it stable. But that water carries organisms from one ocean to another, which is why every modern tanker runs a treatment plant on board. Water passes through a 50-micrometer filter, then through electrolysis cells that generate sodium hypochlorite to disinfect it. Global shipping got quiet ecosystem policy. A tanker painted, plumbed, and tested is still not proven. The ocean has its own opinion. Every ship gets a name and a godmother. She reads a blessing, swings a bottle at the hull, and the yard opens the dry dock gates to let seawater flood in for the first time. Once floating, the ship moves to the fitting out berth for harbor trials. Steering, anchor, windlass, fire pumps, radio, radar, and the whole navigation package get tested piece by piece. A crew of 24 takes over. Then comes the moment the tugboats leave. The ship runs its own engine for the first time under load, feels its own rudder respond, and heads out for open water while the yard watches from the dock. Sea trials measure everything the yard promised. Top speed at full power, turning circle radius, crash stop distance, vibration levels, fuel consumption, noise inside the accommodation block, all logged against the contract. Two years later, that same ship comes home for its first major service. 25 to 30 years of hauling crude is the working life ahead, and the maintenance calendar starts on day one. A crude carrier does not spend its whole life at sea. Every 5 years it heads into a dry dock for a special survey, and the yard opens up sections of the hull that the ocean has been chewing on. On this vessel alone, 20 tons of new steel went into repairs. Plates cut out, replacements welded in, seams ground down and x-rayed. Workers on scaffolding move across the hull for weeks. Painters follow behind. A ship this size is more like a rolling infrastructure project than a machine. It needs a construction crew every few years just to keep going. Inside the cargo holds, scaffolding rises from floor to ceiling. Workers cut out corroded sections, weld in fresh plate, apply new coatings, and check every seam. A crane lowers prefabricated panels through the deck hatches. The dry dock becomes a factory built around one ship, and then dismantled when it leaves. Cargo manifold piping takes a beating over the years. Stainless steel sections get cut out, new spools fabricated in the shop, aligned in place, welded by certified pipe fitters, then pressure tested to the exact spec. Every joint gets non-destructive testing before crude flows through it again. And sometimes the ocean winds around. A tanker that scrapes a shoal or hits an uncharted rock can end up in a dry dock with 100 meters of hull damage that needs to be cut away and replaced. 60 fabricators, welders, and engineers work in shifts around the clock. Torches burn through steel plate day and night, cranes lower new panels into position, and welders climb into confined spaces with breathing equipment strapped to their backs. When the repair is done, the ship sails again like nothing happened. 100 meters of hull that never asked for a second chance. Decks corrode faster than you would think. Saltwater, cargo residue, and constant sun cycles eat through the top layer of plate, so yards regularly cut out sections of the main deck and drop in fresh steel. 20 specialists, cutters, welders, fitters, descend on one repair, sparks flying from overhead as torches slice through corroded plate. New sections are craned in, aligned, welded, ground smooth, and coated. Nobody sees this work from the outside, but the ship would not survive its next voyage without it. Inside the cargo tanks, the work gets even harder. Workers descend through hatches with cutting torches and welding leads, working in confined spaces where every spark is a hazard and every breath comes through a supplied air respirator. Corroded plate comes out. Fresh plate goes in. Every 5 years, back into the yard. Sandblasting, painting, hull surveys, propeller inspection, rudder pintle checks, engine overhauls, 25 days of round-the-clock work before the ship sails out for another 5-year run. Now imagine multiplying that across a global fleet of tankers. One crude carrier represents thousands of decisions: where to cut steel first, which block to lift last, how thick to weld a bulkhead, which paint system will still be intact in 25 years. Every one of these ships, and there are hundreds of them at sea right now, moves roughly 2 million barrels of crude oil per trip, the raw material behind gasoline, plastics, asphalt, jet fuel, and thousands of everyday products. Yet most people have never seen one up close. Where crude carriers go from here is still unclear. Has their size reached its practical limit? Or is the industry still chasing even larger ships? Or will the next generation be defined not by size, but by cleaner propulsion systems and smarter operations? If you found this walkthrough useful, hit subscribe and stick around for the next industrial breakdown. Take care.